Okay, so the steps for this method, just to streamline this, is write expressions or formula for the position and velocity of the center of mass with respect to the world frame. Okay, what this means is for the position, what you do is if you have the homogeneous matrix, let's say that is Hn0, right? It's some point of interest, sense the n being the let me call it Hi, I being the body you're interested in. You would know the position of I in local frame. You get the position of, we call this PCI. You get PC in O. Local frame position, global frame. Yeah, and then the velocity. Okay, there are one way of computing the velocity of C is to just do d dt of PC0. This is method 1, right? You could just do that. Or you could do this way. BC0 would be JV times Q dot. And then omega C is J omega I Q dot. Okay, so this is easy to do for linear. It's not very straightforward to do for angular motion. So, well, maybe it's possible. I've never tried doing this. Omega C0 would be d dt. I think better way to write would be with the R. So what I would do is for angular velocity, you just do R R dot times R transpose, I think R equals S R. So yeah, post multiply. So this would be C0 with a transpose. Okay, so you need to take the rotation matrix, take its derivative, multiply with RC0. It's just so unwieldy. It's like a lot of work, but you can also do it by this method, which we talked about, the Jacobian. It's much easier. Okay, so that's the velocity. The reason why we found the position velocity is because it's going to be used for the second step, which is number 2, is define this quantity called L, which is the Lagrangian, is T minus V, T being the kinetic energy. It is half M summation MI VI transpose VI plus omega I transpose I. So this multiplication is, remember that M is a scalar, but I is a matrix, right? It's a 3 cross 3. So you need to do I times omega I, which will give you a 3 cross 1 vector. This will be 3 cross 1 because this is 3 cross 3 times 3 cross 1. And then you multiply it with 1 cross 3 in same year. This is 1 cross 3, 3 cross 1. So T should be a scalar. It cannot be a vector. Okay, energy is always a scalar. So T is the energy. Oh, kinetic energy. which includes the translation energy and the rotation energy. Now, there is a formula for chains. So this is good if you're doing a simple problem, but for chains, we convert that formula into something which is for using Jacobians. It's much easier. So what we do is we use this expression to convert the formula from V to or omega to Jacobian. So you could rewrite T as follows. So using the Jacobian, can write T as half Q dot transpose. This is the degrees of freedom or the rate of change of the degrees of freedom. Summation goes from 1 to n, all the links. Okay. What we have inside is mi jvi transpose jvi plus j omega I transpose. Now, what sits here is the inertia in the world frame, but that I'll write it as using this relation at R I B R transpose. So what sits is I, so I'll write it as R I B R I B R I transpose J omega I. I'm running out of space. What's left is just Q dot. So this thing here is I, world frame inertia. Okay, so that's the first part. This is the T. What about V? V is the potential energy. V is the potential energy. It's written as summation I equals 1 all the way to n MIG. And then I'm assuming that gravity is in the Z direction, okay? So that will have to change depending on how you set it up. For sometimes planar manipulators, you put it in the Y direction. So just be mindful of that. So you need to put Z of the center of mass in world frame. And then anything which has a potential, like for example, if you have a spring, we've not really talked about spring in this class. There are Q springs or M springs, then you would just put the spring energy also over here. RPI minus spring constant. RPI and RP0 are spring length in relaxed state and spring length relaxed state and spring length when stretched. What else? G is gravity, and it's assumed to be parallel or along Z. Z direction. Okay, so what we've achieved here is we've defined the Lagrangian, which is L, that's the key. it's T minus V. T is kinetic energy, V is potential energy. And so now from these two, we'll get the equations of motion. So the equations of motion are given as follows. Equations motion. D dt of the partial derivative of L with respect to Q dot minus d dl dq was, I'll just call that J. Qj. Okay, so what is all these things? Lowercase q is the degree of freedom. So it could be revolute, prismatic, and then the uppercase qj is the external force or torque. So when you're looking at, if q is going to be prismatic, then uppercase qj would be a force. If lowercase qj is a revolute joint, then uppercase qj will be a torque or moment. So here's example of what qj is. Qj equals x in this case. And here's another example. Here qj is theta. Okay, so anything which you cannot write as a potential would be here. For example, damping, friction, anything will come here. Whatever can't be expressed as a potential. Okay, so let me just illustrate this. I think that equation, getting that derivative equation is sometimes not very intuitive. Like, how do you really do this? So I'll give you a simple example of a single link pendulum. It's easy to derive that by hand. So let's do that. So here is an example of application of Euler-Lagrange equations. So derive the equation of motion for simple pendulum subject to external torque T. Okay, so this is the caricature I have in mind is there's the pendulum. It has an external torque. There's gravity. To keep it simple, I'm going to assume that the inertia is zero. That's just a mass sitting at the edge, and this is actually massless. The rod is massless, but then there's a mass at the tip. Okay, and we know the equation of this we from high school physics, so we could do this with Euler-Lagrange. Let's see how to do that. Okay, so let's define. Oh, I have a problem here. I should not define it as T because I'm already using T for kinetic energy. Let's call that Tm. Or let's call that, I think, yeah, Tm is fine. Okay. Okay, so L is T minus, well, let me do it this way. For this particular case, let's define X, Y. Let's say that the position of this is X comma Y. And you can see from the figure that, of course, I should put the length. This is length L. Okay, so I'll try to write the position of m. So the x position of the pendulum of the mass m is L sine theta, right? This distance, and then y is minus L cosine theta. So this is step one. Find the position. Find the velocity. So x dot is L cosine theta theta dot. Y dot equals minus L. Now the derivative of cosine is negative sine, so it's be positive L sine theta theta dot. Okay, and so if you want to write the velocity, which is a vector, is going to be x dot I plus, you know what, let's write the velocity the way we wrote it. So x dot y, that's the matrix. So we always write it as a column vector, so x dot y dot. So L cosine theta theta dot L sine theta. This is lowercase v. Okay, so that's step one. We need to get all that. The step two is to find the Lagrangian. It's t minus v. So half m v square, or v transpose v. The rotational energy is 0, so we don't bother with that. And then we have mg. In this case, the direction of gravity is the z direction, so mgy. So half m L cosine theta theta dot L sine theta theta dot, sorry, transpose, my bad. L cosine theta theta dot comma L sine theta theta dot. So that's 1 cross 2, and then L cosine theta theta dot L sine theta theta dot minus mg. Now y is minus L cosine theta. You write here. You substitute that here. Plus mgl cosine theta. Okay, so what we can do is we can take the matrix product. You'll get a scalar, so you can see that it'll be L cosine square theta dot L square cosine square theta dot square plus L square sine square theta dot square, and you can use the identity that cosine square plus sine square is 1 to get half m L square theta dot square plus mgl cosine theta. Okay, so this is L. Now let's go to the next step and compute the equations of motion. Now, this is a single degree of freedom system, so you need to only use that equation for qj equals theta. If you had 2 degrees of freedom, 2 links, then you'd use it twice to get the 2 equations. So what I'm saying is this qj is a single degree of freedom, so you'll have only 1 equation. If you had 2 link pendulum, qj will be theta 1, theta 2, and so on. Right? So every qj is basically the degrees of freedom. Okay, so let's take this and compute the equation of motion. Just for reference, step 3, d dt of dl d. Now qj is theta dot minus dl d theta equals all the external forces will come here. So external force is the motor torque. Okay, so d dt. Again, I need to take the derivative of this thing here with respect to theta dot. Okay, so this is where theta dot appears. There's no theta. So when you're doing this differentiation, you need to treat everything other than theta dot as a constant. So theta So when you take the derivative, that is this part, you will get ml squared, sorry, 0.5 or half ml square. And then the derivative of theta dot square with respect to theta is going to be 2 theta dot. And then the derivative of cosine theta with respect to theta dot is going to be 0 because you treat theta dot as a separate variable from theta. Okay, so that's that. And then minus, when you take this derivative now, you need to treat theta dot as a constant and then take the derivative with respect to theta. So the second term stays mgl. The derivative of cosine theta with respect to theta is minus sine theta equals t motor. Okay, and the last step is to take this derivative. So half, well, this 2 and this 2 cancel. So ml square. So d dt of theta dot, rate of change of angular velocity, is the angular acceleration. So that will be theta double dot. Minus or plus mgl sine theta is tm. And so that's the equation. That's the answer. Now, you can check this by putting t equals 0 or tm equals 0. There's no torque. And if you put no torque, then you'll get ml square theta double dot plus mgl sine theta is 0, which means that theta double dot is minus g divided by L sine theta. And this is actually a well-known equation of a simple pendulum. Something you might have derived in high school, right? The negative there means that it's going to oscillate about the vertically downward position. Okay, so now that we know how to do this, let me tell you a little bit about what this equation will actually give you. What is the form of the equation? Because that's going to be very important to know the form of that equation, that Euler-Lagrange equation, so that when we can derive this expression for the pendulum, or sorry, a manipulator using symbolic calculations. So this part is general form of equation of motion for a manipulator. So d dt of dl dq dot minus dl dq equals qj. When you pull this, and I'm going to write this down uh, without deriving it, but you could refer, if you want to see how this comes, you need to go to Spong. There's a book, I think it's in the reference, chapter 6, I think. So it uses basically, what is it's called? It's called using index notation. It basically derives that, assumes that L formula I wrote down earlier with that Jacobian, and then derives that, expands on that, takes the derivative, and shows that you get something which looks like this: m q q double dot plus c q q dot times q dot plus g times q. I'll put something else here. I'll put G. It's not usually written like this, but this will be helpful later on when we try to derive, equals the net torque. We'll call that U. Okay, it's always of this form. Okay. a lot of control is going to be dependent on this form. Because we have this formula for the equations, you can do control, which will do interesting things. So here in this, let's figure out the dimensions of different things. This is going to be n cross 1. Okay, n cross 1. This whole thing is n cross 1. This is n cross 1. Sometimes it's actually, you can just write it at CQ dot. Let's not write Q dot. It actually is there's a Q dot square term there. If you have heard or seen of the Coriolis force, this is something which depends on velocity squared. That comes there. And then this mass matrix is n cross n. So MQ mass matrix. Okay. The key thing is only a function of Q. It's very important. This is a fact we'll exploit later on. It does not depend on velocity. CQ, Q dot is nonlinear Coriolis centripetal acceleration term. Okay, it depends on both Q depends on Q as well as Q dot. Okay, and then GQG is gravity term, and it depends on gravity and Q. Okay, this is kind of only on Q. So this is something which we'll be exploiting in just a bit.